Thank you so much for joining me here today. And what I want to talk to you about today is a system that I built called Codev. I'll talk a little bit about what Codev is, but I think the theme of how do we make agentic coding systems effective. I want to start with 7 principles that I found that are very useful, regardless of if it's Codev or not. I want to tell you about applying those particular principles in a structured way. I'm going to tell you a little bit about the Codev system, the operating system. Let's talk about what Codev is. So it's not just agent harness. It's a set of CLI tools. We'll talk about protocols, infrastructure, and it orchestrates harnesses a structured workflow. The way that I would think about it is it's an operating system for humans, AI, to build software products together. And the same an operating system, except applied jointly to an AI instead of to any one person. And so the goals of this is that often people start with experiences with AI in a very vibe coding way. Type an instruction in, and then out pops code, and they deploy the code, and it works until about 10,000 lines. And what happens very quickly, if you've ever tried to vibe code or use one of the AI apps to build anything, the cliff that happens around 10,000 lines, and many of our projects exceed those 10,000 lines. So AI seems to have a scalability problem that we see. And one of those problems with scalability you'll often find is once you get to about that 10,000 line threshold, you'll have a new PR, and that will cause, it's like bubble wrap. You push in one area and then a bubble pops up somewhere else. You push that other bubble down, so you have this problem with regressions that happens. And then the other thing is, at 10,000 lines, you kind of have this issue with manageable context, right? Because that's a lot of code. You can't just pull that entire code base into your context window, and all of a sudden you have to start to organize things in a different way. So to address this, what I found works, and we'll talk a little bit about the experimental evidence for this, but here are 7 principles for better code that I think all of you may find useful and may actually be worthy of research, because any of these could be something more serious. The first one, and we'll go through them all, but here's like the 1 slide version, and then let's go through each of them. The first one is that it's important to treat natural language exactly like source code. The way that when you have a conversation with AI is ephemeral, but that's the conversation that had your intent, had the AI's understanding, had the clarifications. The code was a byproduct of that. So instead, what if the conversation itself is the source code? And I don't necessarily mean that literally, but what I mean is that there are artifacts of the conversation that are represented. So for example, you could take the conversation and turn it into a specification, or you could turn it into a bug report. And that bug report is the first artifact, but it gets checked in, it gets versioned, updates to the spec or whatever have to be treated as effectively as natural source code. And the reason for that is I think if you don't do that, it feels to me like we're using C. We write very elegant C++ code, we compile it down to assembly, and then we throw away the C++ code. That's what I feel like using normal vibe coding is, right? It's just like the most valuable asset, which is the conversation that led to the generation of the specifications, disappears, right? We would obviously never do that. The second principle is no good model, there's no one good, perfect model. And what you can do is you can play different models against one another, and each one covers the flaws of the other models. And so multi-model review and multi-model development is a very important part of what we do. And so what you find is if you use the 3 leading agent harnesses, each one of them has different strengths and weaknesses. Claude is good at writing, Codex is great at security and finding very detailed bugs. But I was thinking about what Eric said earlier today, about all AI suck, and it's absolutely true, but they suck in different ways. And if there's one lesson from the history of machine learning, it's that ensemble methods work surprisingly well. And so 3 slightly stupid, we used to call ensembles, we used to call them weak learners. And so we can think of these as weak AI models, that when you combine the different AI models together, you get something better than any one of them is capable of. The third one is sometimes the wisdom comes from you and sometimes it comes from the AI. So one day I was discussing Codev with the thing, and it said this beautiful thing. It was the agent that said this. Agents are good at reasoning, but very bad at discipline. And I captured that because I loved it. Because what happens when you have a complex implementation is that the models get very confused about where they are. And it's like they have ADHD or something like that. They go, well, eventually after an hour or two, they're like, what was I doing again? And so what you do is you need to have LLMs and agents non-deterministic, right? But what we can do is we can take a deterministic core and combine it with these systems. So for example, what you can do is you can have a thing that says you are not allowed to advance past stage 1 until you've done these 3 things. In our case, it might be human review, or it might be other agents reviewing it. So Claude will write the first version of the spec, and then we'll have 2 other agents review the spec. They'll have a dialogue about it, and then when they're ready, they'll ask the human, and then the human gives the final approval to do this, right? But to build that system, you can't rely on the AI to do it, right? You can't have soft enforcement. There's actually a program we have that enforces that the AI does that. And it will tell the AI, you're not allowed to go ahead unless you've done this. We talked earlier about regressions. And one thing that I think is incredibly important that's underestimated is testing becomes even more important in the age of AI. We've seen this problem before where the new AI will implement the new feature, but make 3 other features that it's already implemented. And even within a particular execution, if you're building things in a phased way, phase 1, phase 2, phase 3, often phase 2 will unintentionally break phase 1 unless you've written your tests for phase 1 and make sure that phase 2 doesn't break them. So the tests in AI with these agentic harnesses, they're not optional. They're actually they are backstops to prevent the AI undermining itself. And it just gives the AI a concrete signal that it's screwed up. And we knew that. Another thing that I think is a very useful principle that we've extracted from putting these things together is that I very rarely these days edit code. What I will do, or even edit a specification, what I will do is I will annotate. I literally, in some of the tools that exist in Codev, they're designed around annotation, with editing being something you do when annotation is not working for you. And what that means is you have an exchange. It's like a PR exchange. When you leave comments and then the AI reads the comments and then you have a discussion and then it resolves them. But you have this paper trail of what happened there. And so we tend to bias towards annotation. Another thing that's been incredibly important for me to boost the efficiency when using these AI systems is using agents to coordinate agents, right? So let's say that you're building a subsystem, you've divided the work into 5 different components. These AIs sometimes take 10, 15, 20 minutes to run. But it's very hard for you to maintain all of that state about the 5 things that are running in parallel. I personally find that at 2 I can do easily. 3, I start to struggle. By the time it's 4, it's getting very hard and I'm forgetting what I'm doing. So the solution to that is cognitively offload that effort onto the AI. And so what we do is we have this idea called the architect. And the architect spawns builders and the builders do the actual work, in much the same way that you have an architect that drives the creation of a building. And so most of your dialogue, by the time this is in the case, is you talk to the architect, and it's actually the architect that talks to the actual builders that do the heavy lifting, right? And that level of abstraction allows you to scale yourself to be able to do more. And finally, the last principle is the whole lifecycle management. You don't just think about writing the code. You have to think about the testing lifecycle. You have to think about merging. You have to think about verification once it's been merged. So for example, in one of the vibe coding tasks, Claude Code just created the code, but when we're using Codev, it's like, how am I going to deploy? I need to create Docker files for this particular issue. So those are 7 principles that I think as we try to work out how to build these agents and to bring them into our workflows, I think we found out the hard way that these principles are very useful. And I'd love to hear reflections about, are you seeing the same things? Are you seeing the same challenges? And the question you might have is, let's say that we have these 7 principles. Is there any evidence that by applying these 7 principles that would do anything useful? And that brings us to some of the evaluations that we've done so far on Codev. And Codev, of course, is a self-hosted project. It's about 80,000 lines of code. And currently we're on Codev version 3.1. Back in the days of Codev 2, there was a sprint to finish the features. And by using these agents, we were able to, in a 2-week sprint, generate something like 100 PRs. And that's a lot. And fortunately, also, most of those finished autonomously. So the way that it works is we have 4 stages: spec, plan, implement, review. And the spec and the plan, the human is involved. And once the spec and the plan are agreed on, we go into basically autonomous mode, and it will run for a while until it eventually comes back to you for you to review the code. And 85% of the time, it was able to run that whole process all the way through. And as a result of that, the other good thing is we caught a lot of bugs in the pre-merge stage. So roughly speaking, this was a lot of, at least according to non-AI metrics, this is somewhat productive. It seems to be about the equivalent of a 3 to 4 person elite team. So it seems to be, it's very hard, and this is one sample, and I'd love to see ways that, I'd love to learn from your community about how you're evaluating efficiency boosts and productivity boosts with humans in the loop. And I wouldn't literally call this, but there is at least superficial evidence to show that this is, using these set of principles is able to significantly boost the efficiency of a single developer. The second evaluation that we've done is a vibe coding task. Imagine, even though Codev is designed for human agent co-building, you can use it in autonomous mode, right? And what that means is so again, as I mentioned, there's spec, plan, implement, review. We just do the spec and plan and auto approve it. So we just let the agent run loose. So even if all you do is you take Claude Code and you run the spec plan, that process with multi-model review at different stages, you see a huge performance improvement. So we see reductions across the board and improvements, and I'm using a 3-way LLM as a judge approach to decide the quality of the code and averaging them across, and we see improvements across the board for all of the different quality aspects that we've done. And I mentioned earlier the importance of multi-model processes. And again, here we saw different agents finding different bugs and different agent harnesses finding different bugs. And Codex was probably the best at finding bugs, and it's still very good. It still outperforms other systems. But the interesting thing is each one of them found different bugs, including several critical security issues, right? So there was no bug that, there was not. And it caught way more bugs than if we hadn't done the model review. The final eval that we did is Shannon. So Shannon is a project that we're working on. Think of it as a managed, secure, values-oriented version of OpenClaw. It's about 210,000 lines of code. So we've pushed this approach to 200,000 lines of code. And we've talked to people who are using Codev in their companies for much bigger lines of code, but this is one that we can talk about. And as part of building Shannon, we were averaging something like 64 PRs a week. Again, that's considered fairly high output. But what I want to draw your attention to is how that's broken up in terms of the code base. So there's the actual code itself. That's about 200,000 lines of code. On top of that, we have about even more code than tests, right? So even more tests than code. Again, remember the tests are the backstop. So we have more test code than we actually have code. We have multiple different ways of running the tests. And then the other thing is, of course, we have the documentation. And we have almost as much documentation as source code, if not slightly more. And that's by design. And the reason that's important is that allows the AI to work things out way more quickly. So if you have a specification of a feature, you can now just read what the intent was instead of having to read the raw source code and reverse engineer what the source code did, right? This is what the developer was trying to do. When we created this was our goal. Was there a disconnect between the goal that the spec created and the final implementation is a question that can be validly asked, right? And so especially as you scale up, those specifications and the number of times that rather than reading the source, one of these agent harnesses will go to that specification or that plan and read how a feature is implemented is very high. So those specifications really allow the AI to navigate the context of a gigantic code base much more efficiently. And we executed the particular protocols there more than 250 times. And it's a fairly large application with more than 6 subservices. And so one thing you can also do is that you can compare, say, Shannon versus, say, a similar open source project. I chose Hermes because it's in Python. Even though earlier speakers don't seem to love Python so much, it is still the most widely available used system in AI and far better than others. And so the question is just how we can use Python safely. But to give you some idea of the comparisons, right? It's not unusually large. Hermes was built by about 7 people, Shannon by about 2 people. But you can see things like our test ratio is much higher and our documentation ratios are much higher. But the actual size of the code for similar functionality is not out of control. So let's just take a moment here to kind of review where we've been and where we're going. Earlier on, we talked about what Codev was, a set of principles, and then showed the result of applying those principles. but what does that mean in practice? So the way I think about it is I think of Codev as an operating system. In a much the same way that an operating system doesn't write your application, it's a set of primitives that you can assemble to build your orchestration system. And just like there are primitives like files and sockets and processors in an operating system, within Codev, there's 5 core concepts that we need to work through, which is roles, protocols, context, inter-agent communications, and the user experience side of it. A role defines a particular type of agent. It's not what the agent does, but it's like how it works. For example, the 3 roles that we currently have, but you could write other roles, are architects, builders, and consultants. And architects don't write code, and consultants don't write code. Only builders write code, right? And that's by design. But the architect is helping you to decide what to build. And each builder gets its own work tree and checkpointed states. So it's the architects that tell the builders what to do, and it's consultants who review the work of the builders and report back to the architect. So that allows you to expand your mind in terms of what you're doing. The second thing that we have are protocols. And protocols are what enforces that structure that we talked about, the deterministic core for building the code. So we have this idea of protocols, and probably the protocol we use the most is the SPEAR protocol, which is basically you specify what to build, you create a plan about how to build it. That plan includes a sequence of 3 to 10 phases or so. And then each phase, you take a moment and you stop and you do a review. So after the spec phase, you have a human review. After the plan phase, you have human review. You let the implementation run, but during the implementation, AIs are checking the work of other AIs after each phase. And this is enforced. And what we do is we invoke the AI, and if it starts to break the protocol, it's literally not allowed to submit the code until the deterministic core says that the non-deterministic AI has done its job. It's done the reviews, it's addressed the reviews, and so on. And what we've shown also is 2 variants of this. ASPEAR, which is like exactly the same as SPEAR, but there's no human stops at spec or plan. It's literally a JSON file that describes these are the different gates of each stage. So every protocol has a JSON file that describes what each state does. Earlier on today, we heard from Baruz about the importance of memory hierarchies. And again, we have that analogy with operating systems. And just like in operating systems, you have like the cache on the machine, and then you have the main memory, and you have virtual memory on the disk. There's something very similar conceptually called the context hierarchy that we use in Codev. And the idea is that the bottom level of the hierarchy is the source code itself, what's happening, PRs, all of that kind of stuff. At the higher level, you have the specs, plans, and reviews. And we also have the ultimate high level, which is the architecture and lessons learned. So the arch.md file is a description of the architecture of the whole system. The lessons learned is like the things that we've learned in terms of principles. And so you kind of have this idea that when the AI is trying to work out what to do or to understand your code base, they start at the top level, which is mostly stable, lasts a long time, but doesn't change very often, but is very high level, down to the source code itself, which is ultimately the source of truth. But just when we're controlling our context windows, it's much easier for the AI to reason at this level and this level than at this level, right? And having those architects, having this context hierarchy that we build allows the AI to understand the state of the system much more quickly. The fourth thing we have is we have inter-agent communication. So we talked about architects, builders, and consultants. It's great, but how do they talk to one another? So what we've done is we've hijacked the shell that the agent runs in. So imagine Claude, it runs in a shell. Instead of using something like tmux, we have our own thing called Shelper. And Shelper allows different CLIs running in different windows to send messages back and forth to one another, including state information about where they are, when they're stuck, progress, all of that kind of stuff. And even what we've also had is occasionally you'll have architects. Imagine you have 2 sister projects interacting with one another. Often you'll want to send messages between one and the other. And finally, there's the UI aspect to all of this. And there's a UI that we provide. Just very recently, we launched a VS Code extension. So now we have 2 UIs, one web-based and one VS Code extension-based. And it just gives you a view that is consistent with that, with the architect, that thing that you interact with the most being on the left, and then various things that you're building on the right over here. So in terms of future work, I think the things that we're looking at is, so far AI has been very individual focused, and there's not been so much work about how AI can interact across systems. And then the other thing is that the work on Shannon and its 200,000 line code base is forcing us to think about things like injecting a couple of levels into that context hierarchy, in particular metaspecs, which are more like a set of invariants that the code has to meet. And even having multiple architects at once, which sounds contradictory to what we said earlier, one architect. But all of these things are pushing, as we are tackling larger and larger projects, it's opening up the possibilities. In conclusion, Codev is a human agent software development operating system. There's only a very small set of primitives that are available, but that's how we think of it. And it's built on a few key principles. And even if you don't want to use Codev, the three most important principles I would cite is you should treat natural language with the same level of respect as you would treat like source code, if not more. That the way to overcome the weaknesses of an individual model is having models review one another. And finally, we need a deterministic core when we're building these systems together, so that you can make sure that the AI actually does what it's supposed to do and doesn't hallucinate its way into hell. Of course, you can try it. It's available on GitHub. It's Apache 2 licensed. We welcome contributions. And with that, I'd like to hand back over to Ahmed and see if there are any questions. Don't hesitate to reach out if you have anything. Oh, and I have stickers. If anybody wants Codev stickers, come see me afterwards, after the session afterwards. We literally stop the process from running. Yeah, eventually human, but there can be some steps that are not human reviewed. So again, after the specs are done, the human reviews, after the plan is done, the human reviews, the final review is done by the human, but the work is done by the agent, and there are multiple intervening steps there. But yeah. 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 So there's an application called Porch, and it does some of that. It does most of that legwork for us. Of course, the AIs are really very good at getting around the. So, for example, there's a status YAML that describes where Porch is in the process. The AIs, there's that old quote about the internet interprets censorship as damage. What we see is AI interprets blockages as damage and routes around it, right? So what we've seen is they will edit the YAML file direct. So Porch will say, you're not allowed to advance. The others will say, screw you, I'm going to write to the state file directly and update my state so I can bypass you. And so we had to do things like have hooks that would prevent the tools from bypassing the safeguards that we have in place. It's just one of those fascinating things. But yeah, most of the heavy lifting is done by this binary called Porch that at various gates the AI is forced to call before it can advance to the next stage. I think I go back to what Mr. Meyer said earlier today, which is TypeScript is the language that AIs know how to speak the best. For all of their issues, right? The two languages that AI is best of, because there's the most extensive training data, is TypeScript and Python. And so that's what we chose to do it. But Shannon is written in Python. But either way, I'm using a language that Mr. Meyer is not particularly happy with. Either way, he hates whatever I'm using. But that's my yeah.
Very awesome. My own favorite type software from using Rockstar Cloudskate to manage the Android origin working together. So according to your experience, how to effectively manage those Rockstar files in different hierarchy, they update together when they are handled of agents working there, especially for the high level Rockstar. Yep. How do they solve conflict, or how to merge their areas?
Sure. So first of all, we build updating arch.md into the protocol. So before again, in the review stage, the final stage, when a protocol is executing, part of that stage, the prompt that we give the agent at that point says, you must update arch.md. That doesn't always carry backlinks, right? So then what we also have is we have another protocol called the maintain protocol. And the maintain protocol is what you run every so often just to make sure your code base is healthy, gets rid of dead code, useless tests, and also make sure that all three hierarchies of the memory are consistent with one another. So the answer is you build it into your working process, and then that solves the problem for you. And AIs are actually very good at resolving those inconsistencies. On a scale of 1 to 10 of what these AIs are good for, they're about an 8 or 9 in finding inconsistencies in documentation. Cool. All right. Thank you very much, everyone.